Okay, so last time, um, we finished off with explaining how to add two binary numbers, and so now we want to start um, building a machine that can do this. And the first step in this machine is going to be um, a circuit that we want to construct that is able to add two bits together. Um, so if before when we were adding like two numbers, right? Um, this is going to be like this is a bit. Um, and right, our goal eventually would be to build a machine that can add these whole numbers to like the entire number together. But right now, let's start off smaller and build a circuit that can just add two bits together. And the way we do this is we want to consider um, all our possible um, input bits. So, right, we only have these possible cases. And remember that when we do something like um, this, right, we have to do two things. We sum the bits, and then we see if we have to carry over, right? So here the sum is going to be 1, your carry is going to be 0. Here your sum is going to be 0, your carry is going to be 1 over here. So that's what, so our circuit needs to do two things. It needs to output a sum and output a carry. So sum, carry, okay? So with 0, 0, they're both going to be 0. Here you're going to sum to 1, carry nothing. These are going to be the exact same. And then this is going to sum to 0 and carry 1. Okay. And now let's kind of put this into a table just so it looks a little nicer. So your two input bits x and y, and then your sum and your carry. 0, 0, 1, 0, 0, 1, 1, 1. Right, so this is going to be 0, 0, 1, 0, 1, 0, 0, 1. So now what we want to do is we want to build a circuit, right? So what we're going to do is we're going to translate this to a Boolean expression using sum of product expansion. And then from the Boolean expression, we're going to build our circuit. Right, and just to explain a little bit more about Boolean algebra, right, so when we do something like in Boolean algebra like x times y, in circuit logic, this is going to be the same thing as x and y, and then x plus y is x or y, and we have all these different circuits that we can build. So we can go from like these mathematical expressions to circuits. Okay. So, right, and the sum of product expansion is so let's just explain this. Let's just go ahead and do it. So we want to break our circuit into two things. And what we're designing to add two bits together, it's called a half adder. Half adder. Because a full adder, like half adder is just this. A full adder would be doing combining a bunch of half adders together, which we'll look at later on. But anyways, so for this, right, let's just try to translate into a Boolean expression. Okay. So we want to look at first this just our S column here. We want to look at where our output is 1. And our output is 1 here, right? So we see that for S to be 1 here, this is true when X is true and Y of 0 gets negated. And it's also true when, or it's true when X is true. Sorry, when X is, when we negate X and multiply by Y. So the reason this works is because if we change any of these values to what it's not here, right? So like this works if and only if we plug in these exact values to these expressions here. Okay, so now we want to we can reduce this down. Yeah, I wrote this down because I forgot what it was. Into x plus y times x y bar. And we want to kind of prove this first, or show why this is true. This is like the claim. So we can use something called De Morgan's law, which is where we have is equal to x bar plus. Okay, so now we change this expression over here to x bar plus y bar. Now we distribute this out. Right, and now this is one of our Boolean identities where x times x bar is always going to be 0. And we can just kind of look at this, right? All possible combinations that we can put in here are always going to be 0 here. Okay, so these are all going to go away. X and x bar, y times y bar, and then we're left with x bar y plus x. Oh, this should be that. So these are equivalent. And this will make our circuit easier to build, this identity here. So we take this. So this is our S. And then our carry is really easy, right? We're doing the same thing. We look down here, and our carry is true only when we do x times y. So it's x times y. And now we're ready to build our circuit. So in circuit logic, right, this is saying here, I'm gonna write this over here, x plus y, x y bar. This is saying x or y and not x and y. And so now we want to put this in a circuit. And then this one is just saying x and y. Okay, so let's go ahead and build our circuit. So our AND gate is going to look like this, taking in 2 inputs. Our OR gate is going to look like that. It's like a curvy that. And then if you want to negate anything, you just throw a triangle on it. So like if you want to negate an AND, you just put a triangle on it. And this is like a NAND, not AND. But okay, we just want to build this. So first, we want to take in our x and y. Actually, I'm gonna keep this these expressions right here, and I'm gonna erase this just to give me more space to write. So okay. So we have x and we have y. Start off as our inputs. Okay. So first, if we can notice something here, is we're doing x times y, this computation twice. So to save ourselves from using like two different AND gates, we'll just use one. So we'll put both of these through an AND gate. And then this will be the output of this. So this is x times y. The output of this is going to be our carry. But then we want to continue with it. And we want to negate this value. So sorry, this should be like a, I'm like struggling to draw a triangle. Oh my gosh, okay. Well, we're gonna give it one more time and then okay. Okay, that's better. Okay. And this is x times y bar. And then what we also want to do is separately we want to do x or y. So we take this and we feed it through, this is x plus y, so x or y. And then finally we want to join, we want to do a final AND between these two outputs here. So we want to take this and join them into an AND gate down here. So this is going to be x plus y and x this. And then this output is going to be our sum. And so now, like, this looks super abstract. This is like, what are we even doing? We can take these. So just to recap what we've done, we've looked at what it looks like to add 2 bits as just an abstract, like as an abstract table. We've converted them to these Boolean expressions using our sum of product expansion, and then finally we've turned this expansion into logical gates, which we've put together to make a circuit that adds 2 bits together accurately. And so this is the half adder, and so this is really a really good start, because now that we can add 2 bits, we can continue this process and make even more complicated circuits. So we can do a full adder and add more and more bits. And this is very helpful for our calculator. Okay, this was fun. Thanks.